This is Lab 1, observing motion in Newton with Newton's first and second laws for Physics 1. So the purpose of this lab is to apply Newton's first and second laws to measure and graph the x position of a constant moving object as a function of time. So using a video analysis software called Tracker, we will measure the position as a function of time for an object, in this case a marker, and find the best fit line for a graph for both the observed time and position, and then the predicted position as well with a computational model. So the procedure for this lab will be to have a video recording. So in this case, the constant moving object, which is a marker, use Tracker to analyze this motion and get both the x coordinates to calculate the velocity and the time. And then create a computational model. In this case, I will be using Python through GlowScript to predict the future motion and create a computational model that can do that, and compare the observation through spreadsheets. In this case, I'll be using Excel to compare the observed positions and the predicted positions. So the video analysis initial conditions are that the start time is 0, because the time changes from 0 to about 0.567. The ball's initial position is 0.0137. That is the first x coordinate that we are given through Tracker. We can see that in Tracker. So this was the first x coordinate given. And then the ball's initial velocity is 0.3. I will show how that was calculated through Newton's second law. And then the time of the last observation, so the length that the video was rolling, was 0.5672 seconds. So as a refresher, Newton's second law is final velocity equal to the initial velocity plus the net force over mass times time. Using Newton's first law, we can see that an object will not change its motion unless acted on by an unbalanced force. And in this case, we are assuming the net force will be 0. So we can see this in a computational model since the F net vector will be just 0. So we are assuming that the system, which is the marker, is not being acted on and is not having interactions with its surroundings. So we create a loop in the computational model that allows a constant loop under the assumption of no net interaction from the surroundings to predict a new velocity a short time later, and then use that to predict a new position. So this happens again and again within this Python loop. And we can see here that we can apply the formula for the final velocity of Newton's second law. And we can also find the ball position update through our position update formula, or the marker position update through the position update formula. So the ball's initial velocity will be calculated using the initial position and time measurements and the second position and time measurements. So we can subtract these vectors and see the change in position over the change over time. So we get 0.3 meters per second as its initial velocity. And we can use this in the computational model to continue to predict the velocity and the position. A change in the velocity is always 0 because F net is 0. So we see that, in fact, the object's mass plays no role in the prediction. So according to Newton's second law, an object will accelerate in the direction of the net force. And since the force of friction is opposite to the direction of travel, this acceleration would theoretically cause the object to slow its forward motion. However, we are assuming with Newton's first law that the net force will be 0. The system will not be interacting with the surroundings. And using this, we can see that possible sources of error would come from the fact that a marker does, in fact, interact with its surroundings when it's rolling. Forces such as friction and gravity do go into play, so the object cannot actually be in constant motion. However, we assume that the force will be 0 for the sake of the experiment. And then there may also be disparities in the Tracker auto-defining features, so the features are not always accurate. It is simply an estimate. And the time frame used for the computational model, the larger the time frame, the less likely the predictions are to be inaccurate. And since our first change in time is 0.033 compared to maybe a smaller time frame of 0.01, delta t is on the bigger side, which can also dilute the actual predictions. And to conclude the lab, we can see in the spreadsheets that position versus time are actually very similar. So our observed position versus our observed time, they end roughly in similar places. They only have a difference of about 0.02 meters. And we can see that the line for observed position and predicted position are very close. So the model is, for the most part, accurate. And here is the full computational model. And thank you for watching.